So today I'm going to start lecture 30 on FEM in the helicopter dynamics series, and I'm going to further discuss about boundary conditions, specifically the simply supported boundary condition. And also we are going to make some generic comments about the impact of rotation on the differential equation as well as on the natural frequencies. I'm Dr. Ranjan Ganguly. Now, one of the reasons the finite element method became very popular is because it allows for simple incorporation of the boundary conditions. So for example, here there is a simply supported beam. It's simply supported at both ends. Now, if you want to apply boundary conditions here, let's say this is R is 0, this is R is capital R, then going back to our previous three-segment model of the beam, we would set the displacements to be 0. So if we set the displacements to be 0, now remember the first displacement was Q1 and Q7 was the last displacement, Q8 being a slope and Q2 being a slope. So what we do in the global matrices is that we would remove the first and seventh rows and columns from the global matrices, and then this boundary condition would be satisfied. If you had a statically indeterminate structure, such as that shown here, for example, you have a fixed boundary condition here and you have a simply supported boundary condition here, then how you would satisfy the boundary condition is that your Q1 and Q2 would be 0 here because of the fixed end. Remember, Q1 is displacement, Q2 is slope, and Q7 would be 0 because the displacement here is constrained, okay, not the slope. So these three columns and rows of the global matrices would be removed and the boundary condition would be satisfied. So it is easy to handle statically indeterminate structures using FEM. We also saw that once you assemble the M and K matrices, they come out as banded matrices. So some of the terms on the side or very off diagonal parts of the matrix are 0. Now this property can be used in reducing computation cost as well as storage space. There are some books by Bathe which discuss this in detail. Now you are not only limited to cubic polynomials or to polynomials in general. Actually, you can use a higher discretization or higher level of interpolation by bringing in internal nodes within the element. So here I have my usual W1, W1 prime, W2, W2 prime, but we also included W3, W4 and W5. These are three displacement nodes within this particular element. And now I have to increase the order from cubic because I will have more values here. So I would have these values and I can give some values in terms of Q's here. So if this was Q1, Q2, Q3, Q4, this could be Q5, Q6, Q7, and I could create a higher degree polynomial here. Now this philosophy is the foundation of the P version of FEM, where essentially you are increasing the order of the polynomial P by bringing in more and more nodes into the system. And in fact, there are people who use P to the large extent. They may go up to 10 or 15 degree polynomial. The only problem is that sometimes you may encounter numerical issues if you use very high degree polynomials. So we have studied the Galerkin, Rayleigh-Ritz and FE methods, and all these approximate methods can be used to obtain the natural frequencies of the rotating elastic blades. We also see that at low rotation speed, the flexural stiffness term is more important and the effect of centrifugal force is less. Centrifugal stiffening becomes more important at higher rotation speeds. So this is a factor to consider depending on the system you are working on. If you are working on a wind turbine, the flexural stiffness is going to be more important. That is the EI term. If you are working on a helicopter blade or even more on a turbine blade, sometimes centrifugal stiffening can become very important. At very high rotation speed, the beam starts behaving like a string, and the fundamental frequency will approach the rotating frequency. So you can see this mathematically. Let us say your rotation speed is very high, then this term T becomes very large, and therefore we can say that the flexural stiffness becomes very small. And in fact, if we neglect the flexural stiffness in the extreme scenario, that is the EIW4 term here, we would obtain this equation here, which would be totally in terms of the centrifugal stiffening. So what this is telling you is that now you have the equation for the string, which is also known as the wave equation with the tension force. Okay, and so this is very similar to what you have in many physics books where you discuss the wave equation and you discuss a string. The string essentially has a mass per unit length and it has a tension. Now, there's one more equation which is of interest to us. That's the piano string equation, also known as the stiff string equation. Here you would have the flexural stiffness term, but EI is a constant, and you would have the T term, and T is also a constant here. Okay, so essentially the string is stretched by a tension, and that's how it produces nice sound. So this is the equation which is producing the nice sound you hear from the piano. If you were to make T negative, you would get the buckling problem. That's not something we are going to discuss here in this class, but just for your insight, if you were to remove this term and put minus T here, you get the equation which we often use in buckling. So an important part which comes out of all this study is that rotating frequencies are always greater than non-rotating frequencies because you have the centrifugal stiffening, but there is only a very small change in the mode shapes from non-rotating to rotating, and that is why you can frequently use the beam functions in the rotating beam problems. One more important fact which we are going to use in further studies as we tackle response solution is that the natural modes are normal or orthogonal. So essentially that means that integral 0 to r m phi r phi s dr equal to 0 whenever r is not equal to s. And so we are going to use the mode shapes of the rotating beam or the non-rotating beam as the case may be to simplify the governing differential equation of the system and look at the normal mode equations for systems. So that's something we are going to do in our next lecture when we embark on the study of response. So at this point we finish the study of the natural frequency and mode shape. We now know how to get the natural frequency and mode shape for both non-rotating beams as well as rotating beams. So for non-rotating beams, it's very simple. You can use the closed form solution or you can use FEM. And in case of rotating beam, you have to use some kind of approximate method like Rayleigh rate, Scalar-Kin, or the FEM. See you in my next lecture.